100 grams of air just left Mars. Not last year, not a million years ago, right now, and again the second after that. A spacecraft called MAVEN, orbiting overhead, is watching the solar wind strip that air away at roughly 1 million miles an hour. Nothing stops it. Mars has no global magnetic field, so nothing stands between its last air and open space. That single fact reframes terraforming Mars in our lifetime. The planet isn't short on rockets or funding. It's leaking, right now, with no way yet built to seal the leak. That leak has been running for 4 billion years, since Mars's core cooled and its magnetic field shut off. Serious companies still promise a green Mars within decades. The physics measured since 2018 says otherwise. That 2018 study rests on a simpler question first. What actually happened to Mars's air? The root cause is a lost magnetic field, not a lost atmosphere. Mars's field formed the same way Earth still does, from a churning core of molten metal acting like a dynamo. Deep inside a young planet, that motion generates electric currents, and those currents generate a magnetic field around the whole body. That dynamo shut down around 4 billion years ago, once Mars's small core cooled and stopped convecting. A smaller planet loses its internal heat faster than a larger one, and Mars is only about half Earth's diameter. Its core also carries less iron relative to its size, giving it less material to keep churning. Earth's core is different. It's still hot enough to keep turning. It still generates a magnetic bubble called a magnetosphere, wrapping the planet like an invisible skin. That bubble deflects the solar wind, the stream of charged particles blasting outward from the sun. Those are the same particles MAVEN is watching strip Mars bare right now. Without a magnetosphere, the solar wind isn't deflected around the planet. It slams directly into the upper atmosphere, unfiltered and uninterrupted. Gas molecules up there get ionized on contact. The magnetic field the solar wind carries catches them and drags them off into space. This isn't ancient history that already finished playing out. It's a live mechanism, running today, at a rate scientists can measure directly from orbit. That measurement is exactly what MAVEN was built to make. Before MAVEN arrived in 2014, this stripping was mostly inference, not direct evidence. Scientists could see Mars had far less atmosphere than its size and distance from the Sun predicted. They suspected solar wind stripping explained that missing gap, but they couldn't yet watch it happen. MAVEN turned the suspicion into direct, repeated, instrument-confirmed observation, year after year, orbit after orbit. Picture the mechanism this way. A house with every window and door torn off its hinges. You're standing inside, burning as much wood as you can gather to heat it. It doesn't matter how much heat you generate. It escapes as fast as you produce it, because nothing holds it inside anymore. That's Mars without its magnetic field, in one image. Any atmosphere added to the planet today starts leaking the moment it exists. Not eventually, not in some future century, but immediately and continuously, at a fixed and measurable rate. That leak alone would sink any terraforming plan, and the spacecraft orbiting overhead has already measured exactly how fast it runs. That number is about 100 grams per second, drawn from years of direct measurement, not modeling. MAVEN's instruments track 3 distinct places where Martian gas escapes into space. The largest channel is the planet's ion tail. It's a stream of charged particles dragged off the back of Mars, downstream from the solar wind. It accounts for roughly 75% of the total measured loss. A second channel, a polar plume above the poles, adds another 25%. A third, more diffuse cloud surrounds the planet, contributing a smaller remaining share on top of the other two. Together, these 3 channels add up to that 100 grams leaving every second under ordinary solar conditions. Conditions aren't always ordinary, though. Sometimes the sun throws off a coronal mass ejection, a burst of dense, fast-moving solar wind hurled outward from the solar surface. During those bursts, MAVEN has recorded loss rates spiking well above the steady baseline, sometimes by a significant multiple. The stripping surges hardest exactly when the sun itself gets more active. That pattern strongly implies something about the deep past. A younger sun in its first billion years was far more active than today's calmer version. That younger, more turbulent sun likely stripped Mars's early atmosphere even faster than current measurements alone would suggest. This one spacecraft caught the process mid-act with a radar gun pointed straight at the scene. NASA scientists have described the pace another way. Roughly 2 kilograms of atmosphere disappear over a single human lifespan. Too slow to notice by eye, but easy to log by instrument. The reading isn't a single snapshot either. It has been confirmed repeatedly across different Martian years and different solar conditions through multiple full orbital seasons. Every measurement points at the same underlying mechanism. Without exception so far, that consistency matters. It forces a question the popular version of terraforming rarely asks: thickened with what material, and kept there how? Bruce Jakosky and Christopher Edwards supplied the first hard answer. In 2018, Bruce Jakosky and Christopher Edwards published their findings in Nature Astronomy on July 30, 2018. Their method was simple in concept, if enormous in scope. They added up every known and inferred reservoir of carbon dioxide on Mars, not a loose estimate from a distance. A reservoir-by-reservoir inventory, built from orbiter data and surface mission measurements combined, gathered across more than a decade of Mars exploration. The polar ice caps formed the first reservoir, the same ice pop culture keeps proposing to vaporize. Carbon dioxide absorbed into the Martian regolith, the loose surface dust and rock covering most of the planet, formed a second reservoir, carbon-rich sedimentary rock, where CO2 sits chemically locked into minerals rather than sitting loose and free, formed a third reservoir. Jakosky and Edwards then modeled a single scenario. Every gram across all three reservoirs, mobilized at once, released into the atmosphere simultaneously. They used the most generous assumptions available about extraction technology, favoring the terraforming case wherever the data allowed it. Fully releasing the polar ice caps would raise atmospheric pressure by only about 15 millibars. Fully releasing the accessible carbon dioxide in rock would add roughly 12 millibars more on top of that. Combined, even in this best case, the total falls far short of what's actually needed for a breathable world. Mars's current pressure averages about 6 millibars. Earth's sea level pressure averages roughly 1,013 millibars, more than 150 times greater. Martian air today sits at about 0.6% of Earth's pressure. That's thin enough that liquid water boils away almost instantly at the surface. The study's conclusion was blunt. Terraforming Mars with its known carbon dioxide needs technology well beyond current capability. Not because engineering can't scale up with effort and funding, because the raw material simply isn't there, no matter how efficiently it's extracted. The house from earlier had a leak. This planet also lacks the fuel to fill it. Seal every window, replace every door, insulate every wall in that house, and it still won't matter. The fuel in that woodpile only covers a small fraction of what one winter actually requires to stay warm. Jakosky and Edwards weren't describing a technology gap that clever engineers might eventually close with better tools. They were describing an inventory gap, a hard ceiling on available material. Inventory gaps don't close through better engineering alone, no matter how ambitious the plan. They close only if more material turns up somewhere nobody has found it yet, and none has so far. That inventory finding landed directly on top of a proposal that had already captured public imagination for years. Between 2015 and 2019, Elon Musk repeatedly floated detonating thermonuclear devices over Mars's polar ice caps. He framed it as a fast way to vaporize trapped carbon dioxide and thicken the atmosphere almost overnight. He described the idea in interviews and referenced it on late-night television more than once, drawing wide media attention each time. He treated it as a legitimate, if provocative, engineering shortcut worth taking seriously, not just a throwaway line. The appeal was obvious. Skip decades of slow atmospheric engineering with one dramatic, headline-ready act. But the 2018 inventory study wasn't answering a question about explosive yield or targeting precision at all. It was answering something more basic first, a question that comes before any detonation plan. How much gas actually sits in those ice caps to begin with? The answer, it turned out, was 15 millibars worth at best, fully vaporized, with nothing meaningful left in reserve afterward. Detonating a device over the poles doesn't change how much carbon dioxide is stored there in the first place. It only changes how fast you could release that same, already insufficient amount. A faster release of an insufficient quantity is still, stubbornly, an insufficient quantity. This is why the study functioned as a correction, not merely a rival opinion sitting alongside it. It didn't argue against the method itself, or its feasibility, or its cost. It eliminated the underlying premise the method depended on to work at all. The popular proposal assumed the ice caps held enough material to matter at planetary scale. The measured inventory showed plainly that they don't, not by a wide margin. That holds true regardless of how the material gets released, explosively, gradually, or otherwise. Public fascination with the idea lingered anyway, because a dramatic image travels faster than a millibar calculation ever will. But among people actually working the numbers, the nuclear poll's proposal closed the moment that paper published. Not because the idea was too dangerous to attempt or too politically fraught, because it solved a release rate problem that was never the real bottleneck to begin with. If the ice caps can't supply enough carbon dioxide even under ideal conditions, what does a serious institution propose instead? NASA scientist Jim Green proposed shielding the planet itself, not refilling it. In March 2017, Green presented a genuinely different approach at the Planetary Science Vision 2050 workshop. Rather than outproducing an ongoing leak, address the leak's source directly at its origin. Green proposed positioning an artificial magnetic shield at the Mars-Sun L1 Lagrange point. That's a gravitationally stable spot roughly 1,000,000 miles sunward of Mars, where a spacecraft can hold position with minimal propellant. It sits directly in the solar wind's path, before the wind ever reaches the planet itself. A magnetic field generated continuously at that point could, in principle, create an artificial magnetosphere ahead of Mars. It would deflect the solar wind around the planet, the way Earth's own field already does for us naturally. Green's modeling suggested something further too, beyond simply stopping future losses. Over time, with the stripping interrupted at its source, Mars's thin atmosphere might begin thickening on its own. Trapped gas that would otherwise escape would instead start accumulating near the surface, slowly building density. It's a genuinely elegant idea because it targets the actual mechanism from the very start, rather than trying to outproduce it. But the proposal carries its own unresolved gaps, some of them significant. Shielding an entire planet requires a field sustained at one point in deep space for centuries without failure. That kind of continuous output remains far beyond existing spacecraft technology, today or in the near future. No published engineering study has demonstrated a workable power source at that scale. None has shown a deployable field generator or a realistic maintenance plan for equipment meant to run uninterrupted for generations. Green himself described the concept as a starting point for discussion, not as a finished mission blueprint. It answers the leaking house problem in theory, sealing the broken windows conceptually, at least on paper. It doesn't yet answer how you'd build and power a wall that size, 1,000,000 miles from the nearest maintenance crew. Set the ice cap math and the magnetic shield concept side by side, and the real scale of the shortfall snaps into focus. Mars's atmosphere today averages about 6 millibars, as already established earlier. Earth's sea-level atmosphere averages roughly 1,013 millibars, for direct comparison. The popular vision of a green, walkable Mars implicitly assumes something near that 1,000 millibar range. At minimum, it needs pressure high enough for liquid water to stay stable and masks to become unnecessary. Even the optimistic Joukowsky and Edwards scenario tops out around 27 millibars combined at its absolute best. That's the result of releasing every accessible reservoir on the entire planet simultaneously. 27 against 1,000 isn't a rounding error anyone can shrug off casually. It's a gap of roughly 50-fold, using the planet's own known material as the ceiling, not the floor. No extraction technology changes that ceiling, however advanced it becomes over time. The ceiling is set by how much carbon dioxide physically exists on Mars right now. It has nothing to do with how efficiently anyone eventually manages to extract it. This is the number that turns terraforming within a human lifetime into a claim contradicted by direct planetary inventory. A 50-fold shortfall isn't a problem. More funding simply pushes through with enough will. It requires discovering carbon dioxide reservoirs nobody has detected yet anywhere on the planet. Or it requires importing volatiles from elsewhere in the solar system entirely, at enormous cost. Even doubling or tripling every known reservoir through undiscovered deposits would still leave the total short of a breathable target. SpaceX and other private ventures have proposed timelines of a few decades for a livable Mars. Both options sit far outside any near-term mission plan on any drawing board today. This doesn't mean every version of the goal is out of reach permanently. Recent research points toward a narrower, more honest path, still genuinely worth pursuing. In 2026, researchers proposed a genuinely different mechanism aimed at a smaller target. Rather than thickening Mars's atmosphere with carbon dioxide it doesn't have, they turned to something else entirely. Engineered aerosol particles, released deliberately into the upper atmosphere, could trap outgoing heat instead of relying on new gas. Over decades, that trapped heat could warm the surface by tens of degrees, according to the modeling. This approach doesn't try to solve the 2018 inventory problem at all. It sidesteps it entirely, aiming for partial, targeted warming rather than a complete breathable atmosphere. It works toward a realistic timeline measured in decades of sustained, active management. That's a sharp contrast with one dramatic triggering event, like a detonation over the poles. It isn't a refutation of the carbon dioxide shortfall Joukowsky and Edwards identified so precisely. It's a smaller, more technically grounded goal instead, with a narrower promise attached to it. It doesn't require solving the magnetic field problem and the material shortfall simultaneously, in one stroke. Sustained aerosol injection would still need continuous maintenance for as long as it runs. Nothing about it fixes the solar wind stripping described earlier. But warming a habitat's surrounding terrain by degrees is a materially different claim than transforming a planet's entire atmosphere. It's the kind of incremental, evidence-based step that survives direct contact with an inventory study. It never promised more than the underlying numbers could actually support in the first place. So here is where the separate threads finally meet, after everything laid out so far. The magnetic field problem and the carbon dioxide shortfall aren't one obstacle wearing two names. They're two separate, independently confirmed deficits, measured by entirely different methods. Both must be solved before terraforming means what it sounds like it means. One is a leak with no seal available anywhere on the planet. The other is a woodpile without enough wood in it, no matter how it's counted. Maven's mechanism explains why any new atmosphere leaks away immediately, not eventually, once it exists. That live measurement, 100 grams escaping every second across 3 mapped regions, keeps running today. It runs regardless of any proposal currently sitting on paper anywhere. The Joukowsky and Edwards inventory explains why refilling that leak was never actually possible in the first place. Mars simply doesn't have enough material on hand, capping any full release near 27 millibars. Musk's nuclear poles idea shows how a dramatic engineering fix can target entirely the wrong bottleneck. It speeds up a release without creating any more material to release in total. Green's L1 shield concept shows a real, physics-grounded answer to the leak itself. It's still missing the power source and hardware needed to leave the workshop stage. The gap between 6 millibars and 1,000 shows the shortfall in numbers anyone can check independently. It's 50 times over, more than funding alone can ever close through effort. And the 2026 aerosol research shows the shape of a claim that survives all of it. It warms a surface without inventing an entire atmosphere from nothing at all. Together, these aren't 7 separate warnings scattered across different sources. They're one arithmetic, told from 7 angles, and every angle lands on exactly the same conclusion. The lie was never that Mars can't change, or that the science forbids it forever. The lie was the clock people kept attaching to that change. Somewhere past Mars's orbit right now, a spacecraft the size of a small car is still counting, 100 grams at a time. It tracks how fast a planet without a shield gives its atmosphere back to the sun. Second after second, that count keeps running. It will keep running long after this headline about terraforming in our lifetime is forgotten, replaced by the next one.